This is Dr. Khan. I'm going to teach Chem 202 and hope you'll enjoy. And if you have any question, feel free to send me an email at kub@psu.edu. I'll begin with chapter 1, which is on structure and bonding. The structure tells us how different atoms are bonded together in a compound. We'll soon give you examples and talk about both the structure and bonding. We'll begin with atomic structure. Every atom has central nucleus. So this is a central nucleus with protons and neutrons, and these are electrons which rotates around the nucleus. So that's basically how an atom would be, with protons, neutrons at the center and electrons moving around the nucleus. Protons are positively charged and neutrons are neutral and do not carry any charge. On the other hand, electrons have -1 charge. Please have a periodic table in front of you. If you look at hydrogen, you'd see number 1 on the top of hydrogen. For helium, you'd see number 2. Lithium, number 3. Those are nothing but number of protons in the nucleus. What you can see is as the number of proton is increased, identity of element is increased too. So atoms in periodic table are organized according to increasing atomic number or number of protons. Next, we are going to define isotopes. These are the 3 isotopes of hydrogen. This hydrogen, the first one, has, of course, 1 proton. All hydrogen must have 1 proton because that's how hydrogen is characterized. If you have 2 protons, it becomes helium. So 1 proton, but the top number is proton plus neutron. So obviously in this case, 1 proton plus 0 neutron. Then second case of hydrogen, again, since it is hydrogen, number of proton is still 1. The top number is proton plus neutron. Since I already know number of proton is 1, I must have 1 proton and 1 neutron. In third case, I would have 1 proton and 2 neutrons. So what you see here in these 3 cases, number of proton is remaining the same, but the number of neutron is increasing. And that gives you isotopes. So isotopes are elements with same number of protons but different number of neutrons. Almost every element has isotopes. Now, if you look at hydrogen in periodic table and read the number underneath hydrogen, you'll see 1.0079. Now that's nothing but average of all these masses. So they take into account percent abundance. That number 1.079 is pretty close to mass 1 because of predominance of this particular isotope in nature. All these are natural isotopes, and you'd have mostly this type of hydrogen and a very small quantity of the other 2, and that's why average has value pretty close to that of these isotopes. Next, we're going to talk about an atom. An atom has principal level, sublevel, and orbitals. So that's comparable to multi-story building that has floors, apartments, and rooms. Within an atom, you'd expect principal level that's represented by n equals to 1, 2, 3, etc. Just like in a multi-story building, you have floors 1, floor 2, floor 3. So you assign a number. Within principal level, you have sublevels. And sublevels are represented with either a number or a letter. So these numbers start with 0. L value equals to 0 represents S subshell or sublevel. L equals to 1 represents P subshell. L equals to 2 represents D subshell or sublevel. These are comparable to apartments, like you assign some sort of numbers or letters to apartment. You can say apartment A, apartment B, apartment C. Similarly, sublevels are assigned numbers as well as letters, S, P, D. Within sublevels, there are orbitals. So this is how we can quickly find out number of orbitals in a sublevel. That's 2 times L value plus 1. For example, we are dealing with P subshell, which has L equals to 1. So 2 times 1 plus 1 is 3. That means P subshell must have 3 orbitals. And these are the 3 orbitals, Px, Py, and Pz. Orbitals are like rooms. In each apartment you have rooms, and keep this in mind. These orbitals, sublevel, principal level, these are all for electrons, just like rooms are for you or others who are going to rent these rooms in an apartment belonging to a particular floor in a multi-story building. Similarly, electrons are in orbitals within a sublevel that belongs to a principal level and that belongs to an atom. Electron configuration tells us how many electrons are there in a subshell. So for example, H having 1 S1, the 1 represents principal level. That means principal level 1, and then you have subshell S that has 1 electron. Helium has 1 S2, that means principal level 1, subshell S that has 2 electrons. Now let's go to carbon, 1s2, 2s2, 2p2. That means you have 2 electrons in 1s subshell, 2 electrons in 2s subshell, and 2 electrons in 2p subshell. Again, I just mentioned to you that 2p subshell has 3 orbitals, 2px, 2py, and 2pz. And 2 of them have 2 electrons. And this is called Hund's rule, which tells us that if you have orbitals like these belonging to a subshell, they have the same energy, so that means electrons would fill them singly before they start pairing up. That means when you have two electrons in 2p subshell, then first electron would go to the first subshell, then second one will also go to the second subshell, but third one is going to be empty because we don't have any more electron. On the other hand, in case of nitrogen, it would be 1s2, 2s2, 2p3. Each orbital belonging to 2p subshell would have 1 electron. Here we're going to show you how to draw electron configuration quite easily just by looking at position of the element. For example, if I want to write down electron configuration of hydrogen, this is hydrogen and this is line 1. This is 1s1. So I wrote down this periodic table in such a way that if you look on the top, you see S1, S2. On the extreme right, you'd see P1, P2, P3, P4, P5, P6. For electron configuration purposes, assume that helium is next to hydrogen, just for electron configuration purposes. So electron configuration for helium would be line number 1, and then you reached helium, that's S2. So 1s2 is for helium. Let's now look at electron configuration of carbon. This is carbon. So 1s2, I'm done with line 1. And each time you fill in a subshell, subshells are S, P, D, you need to write down that. So 1s2, I'm done with line 1, and at the same time I filled subshell S. Then come to line 2, 2s2, you are here, you didn't reach carbon yet, so you need to go to the right. 2p2, that's carbon. So electron configuration of carbon is 1s2, 2s2, 2p2. In the same way, electron configuration for oxygen is 1s2, we're done with line 1, 2s2, 2p, 1, 2, 3, 4. So that's electron configuration of oxygen. Most of the organic elements would be confined to these electron configurations. However, there are a few cases where you deal with transition elements. These are transition elements, the middle elements. they have d electrons, which would be line number -1. For example, if I'm looking for scandium electron configuration, I'm going to write down like this: 1s2, I'm done with line 1, 2s2, 2p6, I'm done with line 2, 3s2, 3p6, I'm done with line 3. Then in the fourth line I'd have 4s2, and then I need to come to scandium, which would not be 4d, but it would be 3d1. That means line number is 4 minus 1, that gives 3d1. So that's how you get electron configuration of different elements.